Hello, and welcome to today's webinar presented by DME. Thank you for being with us today. I'm your moderator, Christina Fugis with Mold Making Technology, and today's webinar is Optimizing Thermal Management in the Molding Process. Our presenter is Tyler Boss, who's Technical Molding Processing Manager for DME and Millicron. Tyler's going to shed some light on the often overlooked yet critical aspect of preventative maintenance and maintaining mold temperature consistency through the life cycle of a part's production. Now, before we begin, I want listeners to know that you can ask questions during the presentation by simply typing them in the Q&A tab on your screen. Then when the presentation portion is finished, we will try to have Tyler answer each one. Lastly, as a reminder, we are recording this webinar so you can listen to it later online. Now over to you, Tyler.
Thank you, Christina. Good afternoon, everybody. We, DME and myself, thank you for attending today's webinar. If you have any questions or comments, please feel free to put them in the chat. We will get a response to you at the end of the presentation or following. So today, as mentioned, we are going to dive into optimization of thermal management. My name's Tyler Boss. I've been in the plastics industry for a little over 15 years. Currently work for DME. We're taking care of the technical molding and processing situations that we run into. But my background was really started as a process engineer. I graduated college, went out into the real world of molding, injection molding, and really didn't know what I didn't know. Through that, I was introduced to a group, and we were put through a bunch of scientific, systematic molding technologies, and really opened my eyes to what data collection and data can do for process control. So through that, I went through the ranks and climbed from process engineering to production management to general management, as well as becoming an educator and a trainer throughout the Midwest of the U.S., teaching different principles, but mainly systematic molding and implementing new technologies. With DME, people don't understand what DME brings to the table. We bring 80 years of standardization for mold base and molding components. But what we really focus on today, and what really gets me invigorated with what we bring to the table, is our focus on the part. So everything that we do in this industry is really focused around a plastic part. No matter if you're a tool builder, a part designer, somebody that runs simulations, all the way to a molder, we have to make a good finished part. And with the changing situation in the world, and we're all trying to change our responsibility in how plastic is used and then reused, another big piece of what we're tackling at DME is the entire life cycle of the part. So how do we mold this part? It goes out into the industry. It's been used for its function. And then how are we going to reuse that part for the future next widget that we come up with? And it really is based off of what the 4 plastic variables that we all know in the industry of the plastic temperature, how we're going to flow that plastic into the mold, how we're going to pressurize it to get the right dimensions, the right cosmetics, and then the amount of time that it takes to cool that off and start the process again. And within DME, we bring a lot of different solutions to the table besides just a mold base or a mold component. And a lot of it is tailored around that melting, that flowing, that pressure and time. So as we look at heat transfer in our process in injection molding, our mold is nothing more than a giant pressure vessel, and we're filling that with molten plastic. And in that molten plastic, we've got to transfer the heat into the mold, out of the mold, and then start the process again. But I want to step back and explain where DME fits into the value chain of the entire plastics market. So we are a part of a larger company by the name of Hillenbrand. And Hillenbrand has a unique position in the industry by owning a piece, industry expert in each of the pellet production, the tooling, the product processing, and the recycling. And we know that to make a plastic part, it all starts with the resin. But plastic by itself, without additives, is not as useful or is not useful. And that's where our sister companies with the pellet production and the compounding can custom compound in all the additives, all of the fillers to make our part function in the end. Then into the tooling side, the advancements that we're seeing in the tooling are jumping, but we have an industry leader in our hot runner system that's pushing the limits of what we can do and what we can't do with these new materials, as well as all the new tooling components that are brought to the table so we can mold undercuts faster, cleaner, so we can process these exotic materials at high temperatures. And then you get into the processing of the pellet itself and where the mold is sitting. And that's where the market leader like Millicron, leading the market in injection and extrusion, help our customers with the precision manufacturing or molding of the part. And then at the end of that, what do we do with all of our scrap, our waste, and then eventually these parts that are going to come back to be recycled and reused? And that's where we have to restart the process and repelletize and then additives back into it. So DME is part of a larger group that has a broad offering that can really change the mindset of a solution versus just another part that we're going to sell. So looking at thermal management, it's a very complex subject, and there's a lot of people that we take one look at it, and thermal management is about cooling. Thermal management is about heat. But we got to take a step back and really get what the fundamentals of thermal management. And I like to relate it back to the HVAC in our house. So our central heat and air system, for us here in the Midwest, it's 100 degrees outside right now, and I'm sitting in a house that's 70 degrees. I don't like to be 100 degrees in the middle of the summer. So this central system is going to supply air into my house, and it's going to distribute that to each room, and it's going to remove the hot air from my house. And I've got a control system that takes the temperature, sends a signal back to the unit, and then it kicks on and kicks off. This system has been around for decades, and it works very well. But it's very reliant on how well your house was built, who installed it or designed the layout, and then how much insulation do I have in the walls, and what kind of windows do I have in my house. So it's very reliant on a lot of different factors besides just the unit itself. So with technology and energy costs going up, technology advancements and their costs are going down, you're starting to see some different types of heating and cooling systems for our residential homes. One example is in-floor radiant heating and cooling. And this system it's the same principle about keeping our house at a constant temperature, but it can be designed to take up for the extra windows, the insulation properties, and it changes the efficiency of what this system can and can't do. And that's what we're looking at as we look at building molds and we look at thermal management inside of our process. It's not just the mold, it's not just the coolant circuits in the mold, it's the entire ecosystem that we live in, from ambient air to the system that we choose to the control and monitoring that we're going to apply to it. So the advantages and disadvantages of systems really boils down to variation. In molding, that's really why we have jobs. We have variation in polymers. We have variation in temperatures. We have variations in our processes, our equipment. And all these variations have to be managed depending on how critical your part is, what the materials that you're running, the scrap rate and efficiency that you're trying to achieve. And that's where you got to take a step back and look at your system as you're designing it. What do I want out of my system what do I want out of my system from variation? Because as a process engineer, your job is to control the variations that you know of. But if you didn't design in enough windage in the tool or in the part design, your process window as an engineer becomes very small and very slim to make good parts. And that's our job as a solutions provider to the industry. We're trying to open the process windows, reduce your variation that you guys have to deal with on a day-to-day basis so you guys can improve your operational efficiency. And we're going to do that through robust tool designs and the implementation of good process control mechanisms. So designing our tools is not as simple as just picking plate steel, putting coolant lines in, putting the cavities and cores in. We have to really dial in and start to think about thermal transfer and how we want to manage our heat in as we want to manage our heat out. And that's really the foundation of our thermal management at DME, is really controlling the heat from high temperature regions to those lower temperature regions and being able to give data back to the user. So looking at heat generation, it's really one of the 4 plastic variables. It's really one of the first ones that we really spend a lot of time teaching people in the industry about how to melt the polymer efficiently, how to protect the polymer. That is really the important part. And then as we look at the life cycle and the reuse of it becomes even more important. But do we really take it all the way to optimization? And that's where we look at, we melt the plastic with our screw and our barrel and our heater bands on our barrel of our molding machine. We may have a hot runner system that has heaters and on the manifold, heaters on the tips. We've got back pressures, we have screw RPMs, and then we have resonance time inside of our system. And those are very, very fundamental pieces of how we're going to generate that heat. The other one that comes with that is how we flow that material into the cavity. And that shear heat induced by the filling of the material generates a tremendous amount of heat that we have to deal with on the removal. And that's what we get to the heat removal. And the difference, or the delta T, the difference in temperature between the heat input and the heat that we want to get out of the plastic so we can eject it. And in that heat removal, it's really dependent on what type of resin that you're using, because it's only going to give the heat up so fast. And then the tool steel that you chose to use, the water temperature or oil or whatever cooling media that you're using. But you also have the ambient temperature around your molding environment. And then you get into how clean is the surface of my tool. Because that cleanliness of your tool, that film that builds up as we mold, creates another path that heat has to travel through. And then you get into that process times. How fast can we cool the part to be able to eject it? So once we understand the heat generation piece, the heat removal, then we can start to really look at how are we going to optimize. And so to optimize, you've got to understand your inputs, what control parameters that we can manage, which ones do we not have managed, and then put mechanisms around that. And with the optimization, is going to come the preventative maintenance that we have to continue to maintain the asset to the level that it was designed to so it can perform at that given performance level. Which brings in your continuous improvement. And the reason we're kind of diving into optimization requires maintenance and continuous improvement is in the industry, we typically see programs launch in a very linear fashion. And by that, it starts out with a part design that has certain parameters, the form, the fit, the function, maybe it's aesthetics. And from that design, it gets moved over to a tool designer. And then the tool designer takes the part design and modifies this tooling geometry to make it work. And if he can't get it just perfect, he goes back to the part designer and they have a little bit of give and take. From that, somewhere towards the end of that tool design is typically where we see the molders or the processors get involved. And from a processor standpoint, we don't typically get to change the part design. We typically don't get to say, hey, by putting that thick section in the part, I'm going to have a hard time pulling the heat out of that, and I'm going to have a defect because of it. We don't typically get that interaction. And then at the very end of it, the molder or the processor has to deal with the maintenance and the lifetime of that tool, from developing a PM program to maintaining, the coolant circuits, the thermal circuits. And there's not a lot of planning that typically goes all hand in hand with those. So at DME, we're trying to change people's mindset of quit applying this traditional approach and use collaboration. And if you start with the end in mind, which we all know is the plastic part, you bring your part designers, you bring your tool designers, you bring your molder, your continuous improvement group, and you bring them all into the room and you start having true design reviews before you cut tool steel, before you even have a fully developed tool. That way, everybody has input into your part. And there's always going to be a give and take. Perfect world is we would never have thick and thin parts in the same mold or in the same part. We know that's not going to be the case in today's world. But if you bring the part designer, tool designer, and the process or molder in the same room, you can have those discussions where if you have to have that in your part, the molder is going to need a bigger window from a tooling side, or the tool design is going to need a bigger window on their side. So there's a give and a take, and you can develop a process or a control mechanism to track all of these very fine details that will be able to be moved forward as you guys launch your program. So some of the things that we typically fight on a molding side from thermal management is wall thickness. It's a big deal. And if you designed that in your part and you tossed it over to the molder and said, make me a part, if it's non-uniform wall thickness, we have a hard time making good parts all the time. Same thing with fillers or exotic materials. It makes it very difficult to make good parts if we don't have robust designs. And the same thing goes for molders. Not knowing your actual melt temperatures, not controlling your filling rates, your coolant temperatures, your cycle times, having consistency. It's hard to make good parts when you have good designs and good tooling. So all these go hand in hand and they have to work together. But the one thing that we see constantly that gets left out is does preventative maintenance, where does the lifetime of the tool or the asset come into the equation? We know that scale is going to build up in our tools, our coolant lines. It's just inherent with the way the world is. We know we're going to get rust in our coolant lines. We're going to get contamination in there. How do we keep those clean? What is our control mechanisms that we're going to put in place to stop us from making bad parts? So start with the end in mind. it's going to, if you don't, there's risk associated with it. You're going to miss out on your profitability. You could end up with post mold issues out in the field. We see people that have shrinking problems, crystallinity problems. Again, it gets back into decaying mold conditions. If you don't plan for that maintenance, you don't plan for how you're going to execute that preventative maintenance, it's going to happen for you, and you're going to end up shutting the line down potentially. So we suggest people invest in simulations. And with simulations out there in today's world for plastic parts and the tooling, if you invest in material characterization and you invest in knowing what your molder's machine performance really is, you can get very finite, detailed, accurate simulation results that are going to be almost spot on, where you're not having to guess at your process before you put that mold in the machine. And the same thing goes with the tool. If you put in all of the correct steels and you put in the thermal channels, the coolant channels, and you put in the mediums, and you know your performance, you're going to get very accurate results. And one thing we're going to keep saying is you have to invest in water monitoring and control. I don't know how many times I've walked into a plant and, we're making bad parts. Well, do you have water flow? And I watch somebody walk over to the machine and grab the hose and say, yeah, I feel the water flowing through the hose. Is it actually going to the circuit that you want it to? Is it got the right flow? Is the line partially plugged? You don't know anything, and you're flying blind. So you gotta invest in water monitoring. And then that leads into your active preventative maintenance. No matter what we want, we are going to have to maintain these assets, the tools. You can either choose to let it maintain itself when it breaks, or you can plan for it with data and become an active participant and plan it ahead of time. And with that comes the reward. You're going to end up with a better quality part. You're going to end up with more robust cycle times. And then that all falls to the bottom line of your profitability. So our recommendation at DME is really to design with maximum part flexibility. There's a lot of new tooling technologies that allow us to put unique features in molds, from collapsible cores to undercuts, very unique, very thin areas. We have a lot of new technology out there in the industry. But there's also the practicality of putting some of those features in. Sometimes it doesn't make sense when you get into very thin steel to continue to do that. So design with that maximum flexibility. The new technologies are opening the door for improvement, and we've got to embrace them. You look at conformal cooling. It's a great technology. You can 3D print your part, and you can cool it uniformly throughout. It's a great technology, but it's not a one-size-fits-all piece. It's another tool that you should add to your toolbox. As far as the heat input, we haven't seen a big change in how we generate the heat into our plastic and how we reduce our energy usage. But just like our house with insulation, the insulation keeps the heat in, or keeps the cold in and keeps the heat out. The same thing goes with our hot runner system. We can wrap that with insulation, with an eye control insulation, and really capture that heat. That way we're not wasting energy. We're not having to cool the mold plates down. And it's an advancement of where we've been. And we just need to look at all of the new technologies and embrace them. And that's really that holistic view. Thermal management is not just heat. It's not just cooling. It's the entire system. And all the way to insulator boards. If you're running a hot tool, that heat from the tool is going to dissipate into the platen, and you've got to surround yourself with optimum conditions, and pumping heat into a platen makes no sense for your financial benefit or for the mold's benefit. So that leads you into a very comprehensive part design, and bringing in industry experts from the tooling side, from the molding side, from the part design and the simulation side. You're going to end up with a more uniform part. You're going to end up with better form, fit, function, and aesthetics. The problem here that people don't want to address is you're still going to spend time in design. So traditionally, if you did a little bit of design work, you've got cost associated. With a holistic view or approach, you're going to spend more time and more effort in this upfront analysis. It's going to take you longer. It's going to take more money. But what it's going to do is it's opening the doors to allow you to explore these new technologies, and it's going to raise the threshold of where you can achieve optimum thermal stability. But you're going to have to do the upfront analysis, and you've got to do the hard work with the simulations. You've got to have the material characterized. You've got to have the machine performance data from your molders. That way you know how fast you can fill it, how much pressure you have available to use. And that's all part of doing that upfront homework so you can perform with a greater return on investment. So, optimal tooling design, things have really changed with the addition of 3D printing and being able to machine tighter tolerances and new materials. There's new coatings. So we're able to do a lot more finite work than what we used to. So designing complexity in our tool is not the hard part anymore. It's just applying the appropriate technology when we really need it. And take, for example, conventional cooling has been around forever. Straight gun drilled hole water circuits. You may have to use the addition of a bubbler or a baffle if you needed to get water in a specific area. And it's great technology. Thermally conductive materials, heat transfer pipes. All of this works in our standard tooling. It's great to have it. It's simple, but it may not give you the optimized version of what your thermal transfer could be. And that's where the new technologies like conformal cooling allows us to put water circuits in lifters. It allows us to put water circuits uniformly to the surface of the tool steel. The problem with conformal cooling, it's a more restrictive flow path. So when you start adding this new technology, it's not a free lunch, and you're going to have to prepare for the maintenance that comes with it. And that's where having the molder, having the continuous improvement person in the room as you're designing these tools and adding the complexities or simplicities, that they can understand what systems they have to manage the thermal management intent that you're designing into this tool. And that's why we want to get people into this hybrid engineered approach where the best coolant system is what's going to manage that thermal transfer effectively, where we can monitor it, we can control it, and we can maintain it. And it's going to be a combination of conventional, new technologies, and maybe the addition of insulation throughout the tool. All these new approaches to minimizing the waste and energy loss that we see throughout the industry. So once you optimize your tooling, again, running back through simulations before you even cut tool steel, this gets you another piece of data that when you're on the shop floor trying to develop processes, you know how the water was supposed to be hooked up. You know what the temperature of the steel is supposed to be. And you can manage that with your control systems that you're going to put in place. So one of the questions that you always get, we designed it this way. Why doesn't it work? So we designed it with conformal cooling, for example. But over the course of months and years, the productivity of that mold goes down because you've got buildup. Well, there's two rules of thought of you can run to failure on your process, and that's when you start making bad parts, and then you have to initiate corrective actions and troubleshooting and go find out what's going on in your process. Or you could implement a monitoring and control system to catch variations just like this before they become bad enough that they shut your production down or make bad parts. And that's where we really want people to take a step back and go look at your system. You monitor melt temperature, the melt variables very well. You monitor the flow of plastic into the mold very well. You monitor pressure extremely well. What do we really monitor on our coolant circuits of our tools? As a custom molder, we would monitor, the water temperature from the temperature control unit. We would monitor our cycle time and our cooling time, and that's really what we controlled on our water. Were they hooked up the same? Did we use the right fittings? Was it looped or was it plumbed in a parallel circuit? There's a lot of room for variation from setup guy to setup guy and from process technician to process technician. So if you don't have data per circuit, you're really taking a guess of what you have going on inside of your mold. And that's where, with the technology that's out there in the industry, there's no reason we should not be monitoring water flow rates, water temperatures, and the pressure drop between the inlets and outlets of our water channels. It's very simple. There's multiple suppliers of systems out there. And this will monitor how somebody hooked up your water into your tool. Did they do it the same? Do I have the same flow rates? Am I getting the same temperature? And when you start getting that real-time data, and when you trend it over time, you're going to be able to establish your upper and lower control limits. And what those control limits are going to tell you is when I start to see it trend up or down, hey, I'm starting to see some buildup inside of that circuit. Something's not exactly the same. And it could be as simple as a piece of Teflon tape is wedged in there, or a plastic pellet, or it could be calcium, could be lime, could be scale. And there's just all this that could happen in our water circuits today. But we don't take the time to monitor the process parameters. And we're making assumptions that we have problems. And when you want to get into the optimization, you got to get back to the DME principles of define your problem, measure your problem, analyze your data. Then you can improve it and control it. But the first thing is you got to be able to measure it. And that's what I see time and time again as we get into this optimization piece. We don't have the data to really adequately tell us the story of what the problem is. So control your destiny and really monitor your water circuits. I know it's probably not the most economical to monitor 140 water circuits or whatever you guys have, but get back to that design review that you did with the part designer, the tool designer, and you can establish what are the critical control circuits and really hone in on that control of those circuits, especially the restrictive ones. That's the ones you want to make sure you have monitored and controlled. That will be your early indicator of what's a decay in our molding condition. Brings us into reactive maintenance. I lived in a whirlwind. We ran 24/7, and you lived in a whirlwind of mold went down, and you've got to figure out why and get it fixed and put back in the machine. And once we established a real preventative maintenance, and we call it active because we've got data coming back to us so we can make decisions versus reactive or a time-based maintenance system, we were able to track our molds. And right now we're looking at cooling. We were able to track our coolant circuits, and we were able to see when we were trending out of our control limits that, hey, we have water channels that are becoming blocked. They're not transferring heat at the same rate. They have a higher pressure drop, and we need to get that tool out and we need to take care of it. And we could plan that in versus being reactive. And there's nothing wrong with being reactive. It's just going to cost you downtime, machine downtime. It's going to cost you unplanned labor. It's going to be time constraints. And people tend to rush when they're stressed. And that's where we see a lot of labor shortages in the industry today. And not being able to plan our work is really catastrophic when we're putting people under undue stress. So for traditional cleaning of water circuits, there's a host of ways to do it. An acid flush, drill. You could use an ultrasonic bath. All these manual ways of cleaning the system. But it doesn't tell you that you put that system back to the design intent. And as we try to get to this industry 4.0 and this closed loop feedback, we've got to be able to give data back to the system that says we put this coolant system back to the design intent that it came in at. And that's where a system like this cooling care unit goes in, and you hook it up to the ins and the outs, and it goes in and it scrubs those coolant channels with a media, and it goes back and forth, and then it's going to do diagnostics, and it's going to give you a report of how well that channel has flow rate in it, get the pressure drop between them, and it's going to really tell you that you got it back to your design. And you set your program up and you go back to that every time you clean your tool. So whatever you're doing on the maintenance side, you've got to be able to try to get to automation of your maintenance programs, get into recording and feeding that data back into your process, and you will be able to establish a finer, cleaner, active preventative maintenance program. So looking at DME and what we really want people to look at is thermal management, and it really is 5 big pieces. So if you optimize your design through simulation and data analysis, you're raising the threshold of what we can achieve on the molding floor, but you're also giving yourself a chance on the life cycle of protecting the resin and reducing scrap, so we can reuse that material at a future state. And then implement new tooling strategies and designs based off those simulations. Now, whether that be a new water feature from conformally cooled insert to conductive material to insulating properties, investigate them, with your suppliers, and have them really show you the data that proves what these new tooling technologies can do for you. Implementation of a cooling technology monitoring system at each molding machine. And it's, you see, I don't know, go to your shop floor and ask your process technicians or engineers or your quality engineers and see how many times that they've run into a molding machine that had the water kick off and they continue to run parts. You're going to find it happens a lot more than what we want to admit. But if you had a simple monitoring system on there, that was tied into your molding machine, it would alert you before you made tremendous amounts of scrap and help you address the problem quickly versus being reactive. And then it's really just getting into that life cycle performance and really taking stock of your active preventative maintenance and addressing any of your manual processes and try to get it some way to record data at the end of that manual process to ensure that it was put back to design intent. And then that gets back to your tracking baseline versus your investment. And that's the 4.0, closing the loop. That way we can show that by putting these new technologies, putting these process control devices on, that we are actually achieving our desired output. We're hitting our production efficiencies. And we can prove it with our data. So with that, that concludes our presentation today on optimizing thermal management. And we appreciate your time today.
Thank you, Tyler. That was a lot of information. I liked the focus on collaboration, upfront design, using simulation, incorporating all the new mold technologies and maintenance. All, I don't know, you tied that really nicely together. So, I mean, a lot of information. So before we get into some of the questions, I want to remind everybody we still have some time. So use that Q&A tab on your computer to type in a question, and we'll get these through to Tyler as quickly and efficiently as we can. All right. So let's start with, I know we got some questions about particular products, DME specific, but let's see. All right. How do I know whether my water cooling channels have a problem?
It really depends on how your system's set up. Like I said, my background, I primarily was in cavity pressure technology, and we used cavity pressure technology as an early indicator for us. It's a calculated cooling rate, and we could see when we were having a thermal change inside of the cavity. Less expensive option to know that you're having problems. If you're trying to implement a new technology, really thermocouples embedded into the steel is a great way to capture your thermal change. But as far as early indicators, if you don't have any of those devices, typically you'll see it in part quality. Maybe the aesthetics start to change when your water channels start to get plugged. You'll start to see a hotter spot in the mold, and you'll start to see it in the appearance of the part as well as your dimensionals. And that's a great indicator that you've got a problem in your coolant circuit.
All right. All right. Looking more on the engineering side, simulation. You mentioned investing in simulation tools. What kind of simulation tools are most suitable for such large scales? Would you account for any uncertainties in your simulations? For such large systems, there are many variables affecting the performance and hence the outputs of the model that may not be very accurate.
No, and that's where you really got to hone in on your simulation. And that's, with the collaboration, if you work with your part designers and the people that are running your simulations, and you really hone in on that piece of it and tie that back to your molding equipment performance, you will really, I'm not going to say they're going to be 100%, but feeding that back, if you do have a variation that was not expected, feeding that back to your simulation and team and having them rerun the simulation to find out what's going on, what didn't match. I said, personally, I've had very good luck. We detailed out our simulation, and we had our material fully characterized, and we were able to get, within less than 1% of what simulation came out. So we had really good luck, but we had that closed loop collaboration.
Collaboration is key. All right. Insulation. You did mention some insulation boards. Well, we have one with the eye control insulation product. Are there any design factors I should take into consideration?
With eye control, in our hot runner manifolds today, there's an air gap. But it's just like anything. If you're retrofitting a system, it's a lot harder. If you're wanting to investigate insulating your hot runner and reducing that heat loss, we recommend that you do it at the time of a hot runner design. And like I said, we can help you with that. But yes, retrofits are always more difficult than designing it up front.
All right. Conformal cooling, big topic. Conformally cooled cavities and cores, maintenance. Let's get to cleaning. What methods are out there that are available to clean conformally cooled cavities and cores?
So, we recommend that you guys really take a look at the cooling care unit. It was specifically designed for cleaning conformally cooled inserts. And what that pulsating action does is it's pushing water in and it's scrubbing those water channels back and forth. And then it's going to monitor your flow rates afterwards, and it's going to give you a diagnostics reading. And it's going to tell you when you get back to the original set point that you hopefully knew when you brought the tool in. You can use other systems. We haven't seen anything from our end that's comparable to that cooling care unit.
And that was something that's not new. That's been around a while. That was at an MPE I saw, probably 2018.
Yep. No, it's been around, and it's gaining traction. It's one of those devices you don't think you need it until you see it in action, and you clean even just a straight through channel, and you can put a bore scope in the channel, and you can see it has taken off all of the particulate, all of the buildup inside of it. And we don't talk enough about scale, and the problem that scale has is it reduces our ability to transfer heat out of that steel in a very significant manner. And that's what people with hard water, and we really didn't hit on that in the presentation. Knowing your water quality is paramount when you're trying to deal with thermal management. Yeah. It's one of those things. Oh, we treat our water. Well, what are you treating it for? How often are you doing it? Who's checking it? Is it really doing what you think it's doing? And I think that's something that people need to. Another thing to take back is go find out about your water quality.
Big time. All right. Somebody's asking, they wanted to learn more about FlowSense. Can you describe how that system works?
So yes, I'm going to flip back a couple pages real quick and I'll show you. So this is the FlowSense screen. And it's per circuit, or you can do just the one or two circuits. It's up to you. It's configurable, but it captures the in and out. And it's going to monitor your flow rates, so water flow rates with a non-contact sensor. It's monitoring temperature, and it's monitoring the pressure drop. And that's really what you're wanting to see. Sometimes it's not the temperature change that indicates we have blockage, but if you see a pressure drop between the in and the out that's not normal, it's a great indicator that there's something in your line that you need to stop and clean.
Am I correct that a conformal cooling area in my tool may over time become a hot spot?
So, anything can happen, but typically the conformally cooled water circuits are smaller. And then every time you go around a bend, you have a chance of sediment sticking to the non-contact areas and really creating a buildup. But yeah, conformal inserts are notorious for plugging up. Another one, you get into anything that has a bubbler or even baffles if you have bad water. Anytime you put anything in that flow path that changes it, you're creating a chance for buildup to happen.
All right, along those same lines, and we do still have time if people want to enter in any other questions. If the performance of my water cooling channels changes during production, am I at risk of my original setup process conditions no longer being relevant?
So, being out of the medical, disposable medical industry is one of those things. How do you validate that you're cooling at the same rate? And we have a maintenance system that we're cleaning these every so often to make sure that they're clean. But when you really boil it down, do we really check that water temperature frequently enough if we don't have a monitoring system? And the question is no. I had the privilege of working on a machine that had an integrated water monitoring system, and I could see the difference between a 0.5 LPM or GPM change, and it was catastrophic to our production. So if you don't have a system, you're more apt to have a problem. Somebody's changing process variables and they really didn't understand what they were changing. So I think there's a very big potential that you've changed the part without even changing the process setup.
Interesting. Can you share any customer results that could demonstrate any of what you shared today? Results that they've experienced that maybe were impressive?
Oh, absolutely. I mean, and it really depends on what you're looking for, but we'll reach out to you and we can show you from eye control to cooling care to conformally cooled inserts, even insulator boards. It sounds simple, but people still don't use them, which it's crazy. But we have a lot of data from a lot of our customers that we can share with our.
Is the biggest barrier to what you just said just change in general?
Sometimes it's hard, especially when you've seen a lot of change in the industry with personnel. Knowledge transfer has always been a gap in the industry, and we're as an industry, I think, progressed, but we're not there. We don't have that mentorship that we used to have. So there's a lot of knowledge gaps, and I think a lot of it is you just don't know what you don't know.
Huh.
And then we're always trying to work from behind versus trying to get ahead of the game and be proactive.
Is there everything you covered today, not that I wanted you to do a sales pitch or pitch something, but if there's one thing in any of those areas that you would recommend somebody look into today, what would it be when it comes to this thermal management, optimizing it?
So to me, before you optimize anything, you got to know where you're at. So to me, it's water flow monitoring, and that's where I would start. It's easy. The adoption curve is low, and it's going to show you more information in a very short time period than some of the more advanced technologies.
Can you use insulator boards on larger machines, for example, 1,100 ton machines?
I'm not going to say no. You run the risk of, a lot of people with insulator boards, you get mold deflection or the potential to get mold deflection. And that's where some different types of insulation come into play. Typically insulator boards on the outside of the mold, it doesn't have to be. But again, it gets back to how did you design the thermal management system to contain that heat? And, we used to put insulator boards, we ran some magnetic platens. And, having an insulator board defeated the magnetic platen. So we had to run insulator boards that were tucked inside the mold base. So it's just another design consideration that we had to take when we were launching tools.
Again, the upfront design. All right, here's one. Have you used TCUs with VFDs and individual zone management with delta T measurement between zones? It allows for automated adjustments as the flow changes and maintains the desired process until the mold can be cleaned.
So yes. Like I said, with cavity pressure, my background with that, it was really, it's hard for me to say that I allow things to be auto adjusted. We used to call it auto tampering, but when you get a blockage in your line, the flow rates aren't the entire story. So changing the flow rate may or may not get you exactly what you want. And for me, the question comes back is, why did it change? And yes, I've been in manufacturing where we had to get parts out the door and we had to do things that I wish, we had time to go back. But the flow rate changed or the pressure drop changed. Why did it change? And if you don't know why, then allowing something to be adjusted without knowing why is a dangerous situation. That's a non-answer.
Let me see here. Okay. What is the implementation cost of water flow monitoring per injection molding machine?
It really depends on how many circuits you're gonna implement. Like you said, not everybody's going to jump in and want to monitor every circuit. But if you go to every tool, you have very critical areas that need to be monitored. And there's simple systems from one circuit to two, up to 4, 8, and it's configurable. But jump on the DME e-store and you can get a price from what our system costs, and then configure it how you see fit. Or give us a call and we can give you a consult.
All right, we are almost at the top of the hour. We have time for a couple more questions. Tyler, do you have your contact information that you can throw up on the screen as people are looking, or no?
Yeah,
because that would be helpful. If anybody wants to get in touch with Tyler directly, feel free to do that up on the screen. All right, Tyler, from the processing perspective, trying to achieve HDT may be considered a waste of time for many people. Is it in general a good practice to manage appropriate heat transfer levels before ejection?
I would say yes. I'm not going to say we always did that, but yes, trying to get the heat out of the plastic, you're ejecting a large portion of the heat, and it's material specific. But yeah, trying to get to that HDT is the goal. But like I said, I've seen people eject parts out and go straight into a fixture system, and they're working around cycle time. But again, that gets back to, why is the molder doing that? Is it because somebody misquoted? Is it because the tool wasn't built appropriately? And that's where you got to get back to is, yes, we can process around all kinds of problems. It doesn't mean it's right, and it doesn't mean it's going to ever give you that large threshold to be optimized in your real production.
All right. The type of materials that are usually put in the mold: baffles, pipes, cascades, pins. What alloys can you recommend or suggest to improve the heat transfer?
So it just depends on what you're doing. Like I said, we've used, we have a host of materials on our catalog. You see people putting aluminum inserts in for thermal conductivity reasons. It just depends on the material. If you're using a glass-filled material, you've got to get something that's going to withstand those forces, and that's working with DME. our mechanical team, we can sit down, review the material, review the process and pressures, and then come up with an acceptable solution for you.
All right. So speaking of that type of support, somebody's asking, would DME support my company for thermal management project overseas?
Absolutely. We are a global company. We have divisions all over the world. And within Hillenbrand, we have multiple divisions all over the world. So absolutely.
Excellent. All right. So thank you, Tyler. Are there any final takeaways you want to leave the audience with before we sign off?
No, just have a great 4th of July and stay safe.
All right. Thank you, Tyler, again for everything and for answering all those questions. For those who want more or look at the contact information on the screen, you can get in touch with Tyler or DME directly. I want to thank the organizers for helping this webinar run smoothly. And most importantly, I want to thank all of you for tuning in, listening in today. And lastly, visit moldmakingtechnology.com for everything mold making and for all archived webinars, including this one later today. This concludes today's webinar. Again, I'm Christina Fugis with Mold Making Technology. Have a great rest of the day.